Okay, so what we're going to do is talk about the device that is the reference for every voltage regulator I've ever seen. So I can go in here and I can look up a solid state. This is an integrated circuit. So we have so many types of voltage regulators that eventually somebody is going to take, if you use the same circuit over and over and over and over and over again, then sooner or later some manufacturer is going to convert that into what we call an integrated circuit. Y'all know what an integrated circuit is? What's an integrated circuit? What'd you say? Yeah, well, it's an entire circuit put on a single piece of silicon. They make the whole thing on a single piece of silicon. So used to, you'd go out and look at a radio, and it would be tons of transistors and all kinds of stuff inside that radio. You go in there now, and it's probably got one big old IC in there. The whole radio, since radios have been around so long, they did what? They integrated. So voltage regulators have been around on voltage regulation. There's been a need to regulate voltage for years, right? You understand? So eventually they come up and they make voltage regulators. So we have a lot of voltage regulators out there, what we call three-terminal regulators, but they're integrated circuits. And one of the main ones is the 7800 series of voltage regulators. And we should have the data sheet on one of them. Hopefully it's on Blackboard. This is the one we look at. Now normally on an integrated circuit, you're not concerned with how it works, you're concerned with what it does. Because if it don't do what it does, you're not going to take it apart and fix it, right? So here's data sheets. Let's see if we got the 7800 series up here. If we don't, these are very, very popular voltage regulators. Yeah, the 7800 three-terminal voltage regulator. And here's the data sheet. And we don't need to understand that. We just need, this is the actual schematic. Well, what's that the symbol for right there? Zener. And what's that the symbol for right there? Zener. So it means even though this right here is a voltage regulator, so we can buy these things. We can buy them, the 7800 series, or we can buy a 5-volt regulator, a 12-volt regulator, or a 15-volt regulator. And they're real easy. That's their number. See, an LM7805, an LM7812, and LM7815. And I put these suckers on an unregulated power supply, and by George, it's going to give me 15 volts, 5 volts, if I give it enough unregulated voltage, right? You understand that? I don't need to know how it works. All I need to know is what it does. And it's really simple. All that electronic circuit, we got an input pin. Our unregulated input comes in here. This is our common, and then our regulated output comes off there. I put this into a circuit. I give it enough unregulated voltage. I get 5 volts out of it. But the reference voltage is set by a device called a Zener. So this is what we'll look at. We'll look at Zener. So I can make a regulated power supply myself. Very simple. Just requires math, right? Which I love math. It's all in the math. So this is a common VI characteristic curve for a diode. And this would be true for a Zener diode too. Zener diodes are all made out of silicon. I've never seen a Zener diode made out of germanium. So that means if we forward bias the thing, we come up here and we get around 0.7 of a volt, it's going to start conducting. And then it's going to slant a little bit because it don't stay exactly 0.7. So far it's the same. If we reverse bias it, as soon as we reverse bias it starts conducting that leakage current. And then it comes over here and then it hits this reverse breakover voltage. And normally this right here is what? That's not good. But guess where we operate the Zener at? We operate the Zener over here. but we're gonna have to protect it with a resistor. But this guy is designed to handle a pretty good deal of reverse current. So a Zener diode is normally operated in reverse bias. Now, if we can operate it in reverse bias, then its output across the thing will remain fairly constant, even though the current through the Zener is changing. And that's what we're going to do. We're going to use that right there as our reference. So, it's a silicon p-n junction. The Zener diode is specifically designed to work and operate in the reverse breakover region. In fact, this is where it's designed to work at. So if you reverse bias a regular diode and you let it break over and you don't protect it, then it's going. So we broke over that 1N914, but we protected it with a 1 megohm resistor. Now remember that. If we didn't have that 1 megohm resistor in there and I broke it over, what would happen? It would pop just like that, right? So we're going to have to protect this thing with a resistor, but it's not going to be a 1 megohm resistor. These guys can handle up into milliamps, which is pretty neat. We have two types. We have avalanche and Zener. So avalanche is what they're talking about on a regular diode. So we're not going to call this Zener voltage. What we're going to call this voltage is we're going to call it VZ. And this stands for the Zener voltage. So if I say I got a 15 volt Zener, then that's what we're talking about, VZ. Are we okay? So, okay. Zeners break over at low voltages. So we can get a 5 volt Zener, we can get a 12 volt Zener, we can get a 15 volt Zener. A regular diode is going to have breakovers in the hundreds volts, 1,000 volts, right? You understand that? As the reverse bias increases, the reverse current remains very small until we reach what we call the knee. So y'all understand the knee, right? So we call this right here the watt, and we call this the knee. Now once we get past the knee, this voltage is relatively constant until we come down here and we burn it up. So somewhere down here we're going to burn the Zener up. Because we're dealing, if we're pushing current through a voltage, remember power is equal to V times I. So one of the ratings on the Zener, so when we start looking at solid state devices or even electronic devices, just about all devices have ratings, right? So what's the three things we rate resistors in? So if I go out and buy a resistor, I'm going to have to tell that person, or even if I order a resistor on the line, I'm going to have to know three things before I can order that. What's the three things I'm going to have to know about the resistor before I can order one? What's the three things I'm going to have to know about a resistor before I order one? One should be obvious. What's the next thing I need to know? Watts. What'd you say? What last, Scott? Yeah, the tolerance. That's the three things I need to know. So I can't go to Forbes and say I need 100 ohm resistor. Right? I'm going to say, okay, what wattage rating do you want on that? Or what tolerance do you need, right? You understand that? So that's the three things we need to know. So we can buy 5% tolerance. We can buy 1% tolerance. If I buy 1% tolerance and I could get by with a 5, then which one's going to cost more, a 1% or a 5%? 1% is going to cost a lot more. So you need to know that, right? You understand? So a Zener has got a wattage rating because it's dropping a voltage. We're putting reverse voltage on it. So if you exceed the wattage rating on the Zener, what's going to happen? So two things it's going to have. It's going to have a voltage called VZ. This is its regulating voltage, and it's going to have PZ. So that's two things in the data sheet, plus other things we need to look at. It's going to have a tolerance too, right? Just about all your solid state devices have tolerance. So that's one thing they're going to ask you if you go and say, well, I need a 15 volt Zener. They're going to say, well, what power do you need? What power rating do you need? And then tolerance. Effects begins at the knee. At this point, the current increases rapidly. The breakdown voltage remains what? Essentially constant. A Zener diode keeps an almost constant voltage across its terminals within a certain current range. So we got two things that we need to know. We have what we call IZK. What do you think IZK stands for? So IZ, what would that stand for? This is going to be the Zener current. So what would IZK stand for? Good. So this is the Zener current at the knee. So to make this thing regulate, we gotta operate it at more current than the knee current, right? Does that make sense? That makes sense. And then IZM, what do you think IZM stands for? It's going to burn up sooner or later. Sort of. So IZ max. But yeah, meltdown would be good. So IZ max. So as long as we operate the thing between IZK and IZM, it's going to regulate pretty good. Not perfect, but pretty good, right? You understand that? So that's what we need to do. Operate it. We called it below the knee, and we call it above IZM. So this is what we're looking at. So here's the knee current. Here's the maximum current. Now on the data sheet, notice it varies over a range, and this is VZ right here. So VZ varies over a range. So what they do is they choose what they call a Zener test current, IZT. So this is given in the data sheets. And this is where VZ is set. So if they say it's a 15 volt Zener, that means it's 15 volts if you operate it at the test current. If you operate it below the test current, you'll get a little less than 15 volts. If you operate it above the test current, you get a little more. Does that make sense? Everybody okay? So they give us this. They give us this in the data sheets. They give us this in the data sheets, and they don't give us this. But they give us this. So the watts rating is the maximum rating we should ever let the Zener dissipate. So how would I calculate IZM? So they give us this. They give us VZ. What's VZ? We call that the what? Zener voltage. They give us the watts. So how would I figure out IZM? No, I is equal to P over V. So what we'd do would say IZM would be equal to the watts max, yeah, divided by VZ. That's what we calculate. For some reason, they don't give that. I've never seen a data sheet where they give you the maximum current, but they give you the maximum power. So if you know the Zener voltage, you know the maximum power, then you can calculate the maximum current, right? Are you okay? Everybody okay so far? IZK, the regulated Zener must always operate above more than this current. IZT, this is the current flow where VZ is established. The circuit should be designed to regulate as close to this as possible. IZM is operating above this current will damage the Zener. The current is not given in data sheets, but it's calculated by taking PZ max and divided by VZ. Everybody okay? Zener is equivalent to a voltage source. Zener is equivalent to a voltage source in series with a very small resistor. The Zener impedance can be calculated by, and we talked about this, right? So anytime you see delta, it means a change. So we're not going to be concerned with Zener impedance. But what you do on Zener impedance is you'd measure the change over a range of voltage. Then you would measure how much the current changes over that range. And you divide the change in voltage by the change in current, and that would give you what we call the Zener impedance. But we don't need to do that because it's specified where in the data sheets. We okay? And this is like the resistance of the Zener. We'll never use this. So this is basically what the Zener looks like if it was perfect, if it was ideal. So what we're going to do is we're going to come over here, and if I'm going to break this thing over, I'm going to have a resistor. Everybody understand that? Okay. And then what I'm going to do is I'm going to come over here and I'm going to put my Zener, and we're going to reverse bias the Zener. So normally the Zener is operated in reverse bias. If we forward bias it, it acts like a diode. So right now we're going to put this plus DC. Put my Zener in like this. And this is common. Now what we're going to do is we're going to generically refer to this as RS for the series resistor. In fact, we'll just put that right there. So in real life, it's going to be called R5, R15, depending on the circuit. But generically, we're going to call this RS. So what that does is over here, I could have this changing. Let's say it's changing from 15 volts to 12 volts. And this over here is a 10 volt Zener. So VZ is equal to 10 volts. Well, what the resistor is doing, it's going to drop the difference between what we put over here. So this is unregulated, right? You understand that? Over here, this is going to be regulated. So, and we'll figure out. So one of the main things on Zeners is figuring out what size resistor to use right there. We can't just randomly choose a resistor. Now, if I come over here now, if this thing here is sitting here and it's got 10 volts on it, if I put a resistor over there, what's going to be across the resistor? How many volts is going to be across the resistor? 10 volts. Because it's in parallel with the Zener. So the Zener is sitting there maintaining 10 volts. So whatever we put in parallel with it, it's going to see 10 volts. So, and I didn't put the size of the resistor. Of course, it's going to mean something because the more current we pull, the more voltage this resistor over here is going to drop. So when we regulate, we're going to have to set, okay, what range of resistors can we put over there? So it's just like this power supply right here. It's 20 volts at, I can't read this, guys, at so many amps. Well, what if I try to make it draw more than that amperage? So let's say it's 2 amps. What if I try to get 5 amps out of it? What's going to happen to the 20 volts? Well, the power supply is going to go out of regulation, right? Because it's going to regulate at a certain voltage, and then it's going to have a tolerance that it can regulate. So if we try to get more current out of this thing than it can handle, then it's going to go out of regulation, right? You understand that? But as long as I don't put a resistor out there that requires too much current, then this guy's going to regulate pretty good. The trick is choosing the size of that resistor. If I put one in there too big, it's not going to regulate. If I put one there too small, the Zener's going to. So one of the little things that we're going to learn is how to calculate that what? That resistor. Whose laws are we going to use? Ohm's law. R is equal to V over I. Okay. All we got to do is figure out the V and the I. So by the way, there's no new formulas that we'll learn for this guy. Well, that's not true. They're going to appear new, but there's nothing but Ohm's law. All we're going to do is figure out what am I going to use for I and what am I going to use for V. Right? You understand? When I calculate power, what am I going to use for V and what am I going to use for I? How do we stop with that? So we'll calculate this whole thing using Ohm's law. Just so if you don't know Ohm's law, you're screwed. So here's what we're talking about. So characteristic curve, as long as we keep it between those ranges, the thing is gonna operate really nice. Is the output gonna change? Yes. But it's gonna be pretty constant, right? You understand? These things will regulate around 2%. So that means they'll 98% regulation. So that means a 2% drop if we don't go all the way down to the knee and we don't go all the way to IZ max. If we operate it around IZK, it'll work out really good. And this is calculating the resistance. Data sheet. So it's going to give us the impedance. It's going to give us the temperature we can operate on it. It's going to give us the power. Now the problem is when they give us the power, it's going to be at 25 degrees centigrade, which is about 72 degrees. So what they'll give us is they'll say, okay, if you operate that sucker above 25 degrees, then it's not going to be able to handle the power that it's supposed to handle. So we call this die rating. So in electronics, even in residential and commercial wiring, you do what we call die rate the wire. So we have an ampacity. So we look up in the chart on ampacity, and it says a 12 gauge wire is rated at 20 amps. And then they start saying, well, if you run this through a boiler, if you run it up in the attic, if you run it through this, then you're going to have to die rate that, which means you have to drop it down a certain amount depending on what that conductor runs through. Now, believe it or not, house wiring has been die rated so much that you probably won't run into any problem. It's when you get into commercial applications that you're going to have problems, because a 14 gauge wire, if you look up on a American wire gauge, a 14 gauge wire is rated at like 30 amps. But NEC rates it at 15 because it's inside a jacket. It's inside an insulator. It's inside a jacket. It runs inside your wire. It runs into your roof. So odds are in your house, you're not going to have to worry about it. But you get into commercial wiring where you're running these gauge wires, and you're going to run it a real long distance. So what's the link where you have to start die rating for length? Do you know? So like if you're going to run a yeah. So over 100 feet, if you're going to run it over 100 feet, then you're going to have to die rate it for what? For length. Yeah, over 100 feet. So I'll ask God a lot of these electrical questions. He's an electrician. If y'all need any electrical work, God's license. So that's the same thing true with the Zener. So if we operate it above this temperature, we're going to have to do what? We're going to have to die rate it. And that's going to be in the data sheet. Zener test current is going to be in there, the Zener voltage, and then IZ max is not in the data sheet. So what will we have to do about that? We'll have to calculate it, right? Everybody okay? So that book talked about Zener test current. Your book don't even talk about Zener impedance at all, so we don't need that. So this is a typical data sheet for a Zener. So this is the 47,000 series. This goes between 4728 to 4764. And the only thing that really varies is your Zener voltage. So here's our Zener voltage right here. This gives us our tolerance. So see that? So this guy right here could be between this 3.315 volts up to 3.4 volts at Zener test current. But normally when we do our calculations, we do it for the typical. So a 1N4728 is a 3.3 volt Zener, and then they got them going all the way down to 100 volt Zener, which would be a 4764. The A is a 5% tolerance, by the way, and that's somewhere in the data sheet. So they got a 1N4728 series, but it's not the A. So the A is the actual tolerance. Here's the Zener test current. So this will be concerned with this. Here's the knee current. In fact, we'll figure out which one. We got two of them, but we'll figure out which one we need to use. So this gives us the impedance. This calculates the current at the impedance. So we're not concerned with that. We're going to be concerned with this. So on all these right here, we need to operate them above 40. What unit is that? Oh, this is IZK. This is IZK right here. I'm sorry. This is milliamps. So we're not concerned with that one. We're not concerned with this one. We're not concerned with that one. So when we design these things, we're going to be when we calculate that resistor, we're going to be concerned with this, and we're going to be concerned with this right here. What's this? So this is a 1 watt Zener. And then, of course, this is we dye rated right here. We'll look at that later. So it says above 50 degrees, we dye rated 6.67 milliwatts per degree. So that means if I went up to 75 degrees, then we would take 25 and multiply it by that, and then subtract that. Right? Y'all understand? Because it says above. Y'all understand that? So this is a data sheet. So when we do this thing, we're going to look at, of course, we're going to have to use the power rating. We're going to have to use the knee current. We're going to have to use the Zener voltage. That's three things we'll really need. I guess this one's up on the platform. Photodiodes can be used for voltage regulation in low current applications. It takes a varying DC voltage unregulated and keeps a relatively constant DC output. The Zener can only work over a set range of current. We got to go above what? If we go below the knee, then it's not going to regulate. So when we say below the knee, we're talking about less current. And if we go above IZM, what's going to happen? It could burn up. Everybody okay? I lost anybody. So this is showing us a Zener. We'll set one of these up here, probably next class, and look at it. We'll try to be in lab most of next class. Any voltage applied to the Zener that is above will be a short circuit. A resistor that is connected in series with the Zener, we'll call that RS, is required to drop the difference between the unregulated and the regulated voltage. Calculating the size of this resistor is really important. So here we've got a device. So what sets the current flow through a resistor? How much current? How do we calculate the current flow through a resistor? I is equal to V overall. So that means once we've got a V, then we get the same current if the R don't change. What you're going to find out with the Zener is dynamic. It constantly is changing its R to maintain a constant voltage. So even though the current flow through the Zener is changing, the voltage drop across the Zener does. So that means that Zener is dynamically adjusting its R to maintain a constant voltage, which is really, really neat. So you could do it with a pod. You could take a pod and you could put a load out here and you could adjust it up to get more voltage or adjust it down. So what you're doing is you're changing the ratio of the voltage on that pot, right? You understand that? This is going to do it automatically. So this is the basic Zener circuit right here. So over here we put unregulated in. Over here we get regulated out. Zener is put in there how? Reverse bias. And there's that RS right there. And so we call that the series dropping resistor. If that resistor wasn't in there, that Zener would flat burn up. If it's too big, it'll drop below the knee. It'll go out of regulation. If it's too small, we'll go above IZM. We'll go below the max, IZM, and we'll burn it up. So what formula are we going to use? What do we need to know about that resistor to calculate its size? We need the voltage drop across, right? And we need to know the current flow through it. If we know those two things, then we can come up with a size resistor. Everybody okay? So let's say we're coming over here just like before, and I'm putting 15 volts. This input is changing between 15 volts and 12 volts. So this would be like when I put unregulated. So remember, when you do the unregulated, what you end up with is you end up with a voltage that looks like that. And as you load it, it comes up here and drops. So what we need to know is we need to know that valley voltage of the maximum it'll ever be. And that's what we'll use right here. And then this right here would be that peak. And that would be what we regulate. And if this is a 10 volt Zener, so VZ is equal to 10 volts, what's that resistor going to have to drop? So what's the voltage drop going to be across that Zener? I mean, across that resistor. What? It's going to vary. It's going to vary between a range. What range is it going to vary? Huh? No, it can't. Kirchhoff's voltage law says the sum of the voltage drop in the series loop have to equal to applied voltage. I can't drop 10 volts right there and drop 15 volts right there. 10 volts plus 15 is 21 volts. Y'all understand that? It can't be that. What's it going to drop? What's the resistor going to drop? I got 15 and 12 over here. I got 10 right there. What's that resistor going to drop? Huh? It can't drop 25. Let's look at Kirchhoff's law. I'd say 25. I got 15 volts of maximum I have applied. Kirchhoff's law says the sums of the voltage drops in a series loop have to equal to the applied voltage. So I'm going to say 25. I'm going to add 10 to it. That comes up and gives me 35 volts. I've only got 15 volts to work with. It can't be it's Kirchhoff's voltage law. I'm getting excited, guys. I'm not pushing it. It's going to drop, it's got to drop the sum. Okay, so I got 10 volts out here. I got 15 and 12 volts over there. What's the resistor going to drop? It's going to drop 5 to 2, right? You understand? So it's going to vary between 5 and 2 volts. So when the input's 12, it's going to drop 2. When the input's 15, it's going to drop 5. Y'all understand that? So the current through the resistor is going to have to change. Because if it's a certain size resistor, right, you understand. If it's going to drop 5 volts, it's got to have more current flow through it. If it's going to drop 2 volts, it's going to have less. But it's going to always drop the difference between the Zener voltage and the unregulated. Who's going to adjust its current? This guy right here is going to adjust its current and try to maintain 10 volts. So if the voltage tries to go up, Zener current is going to go up automatically. If the voltage goes up to 15 volts, Zener current is going to go up. Its resistance goes down. If it drops down to 12 volts, Zener resistance is going to automatically go down. So this guy here is pretty dang neat. So it maintains a constant output even though the current fluid changes. And the current automatically changes. It's not me adjusting a rheostat, right? You understand? It automatically changes for me. Automatically. So its resistance is constantly changing. Okay, but this guy here would be no good unless I came over here and hooked up Watt over here. I need to hook up some type of load, right? Okay. Now follow me so far. And of course, what we're going to look at here is a current load. So what current do y'all want to pull into this? So let's say 100 milliamps. And since it's fixed, it's a regular resistor, we'll just put 100 milliamps. Okay. But I see this dot right here, and as soon as I see that dot right there, I think parallel. So what's different in a parallel circuit? So this resistor right here, all the current, so this resistor is going to have to handle two different currents. What's the two currents it's going to have to handle? And we'll draw it, we won't draw electron flow, we'll draw a hole flow. So we come up here and hit this dot, it's got to handle this Zener current, and it's got to handle the load current, right? Y'all follow that? This makes sense. So that's why it's called a series resistor. Do I ever want my Zener current to go to 0? The Zener can only work over a set current range. We're going to have to make sure we put more current in it than the knee current. And we're going to have to make sure we never put more current than the maximum current, right? You understand? Does that make sense? So where would I find the knee current at? So where would I find the knee current at? Where would I find the knee current at? I would look it up on the wall. Data sheet. So let's make up one. What knee current did we look up? Let's say 5 milliamps. Let's see if this will work. So if it's a 1 watt Zener, we'll have to lower that down a lot. So let's say it's a 1 watt Zener. I'm going to divide this by 10. That's the Zener voltage. So what would IZ max be equal to? 1 divided by 10. 110. 100 milliamps. So let's don't make that 5. Let's make it 1. Because we don't want to operate at half the current. So this is IZK. This is IZ max. So we want to operate it above IZK. So what do we need to do? So I know we got to operate. So right now, what would the current flow be through my series resistor? According to Kirchhoff's current law, what would this current flow be? What would I need to know the current? What would the current flow be through RS right now? If I had 1 milliamp of Zener current and I had 100 milliamps of load current, what would be the current through the resistor? What'd you say? Kirchhoff's current law. Kirchhoff's current law says the sums of the current in the parallel branches have to equal to current in, right? You understand that? Has to equal to the sums of the current. So that means right now, then, we would have 101 milliamp going through that resistor. Everybody okay? All right, so where'd y'all learn all these laws at? Where'd y'all learn these laws at? Kurt, where'd y'all learn these laws at? Where'd y'all learn Ohm's law at? Kirchhoff's laws? Where'd y'all learn Kirchhoff's laws at? DC. So undoubtedly we didn't learn them, did we? So what we need to do though is we need to operate this thing above IZK. So what voltage are we going to use up here to calculate the resistor? Are we going to use 5 volts or are we going to use 2 volts? So I got to use one of those voltages. We choose one, the other one takes care of itself. Huh? No. We're trying to calculate the resistor. The resistor never sees 12 volts. The resistor never sees 15 volts. That resistor is going to see 5 volts. It's going to be something between 5 volts and 2 volts. And this is a common mistake. People, when they calculate that resistor, they don't think about Kirchhoff's voltage law, right? They don't think about, okay, my Zener's dropping 10 volts. That resistor there is not going to, it's going to drop the difference. And what's the function of RS? Well, the function of RS is drop the difference between the unregulated and the regulated. So you got to have, to regulate, you got to have more voltage in your unregulated than you're regulating at. So that means if this was 9 volts, the dang thing would go out of regulation. So my minimum unregulated voltage has to exceed my regulated voltage, probably by about 10%. So we're going to calculate that resistor, which way, and we always got to operate above IZK. So we don't want IZK to go down, we want IZK to go up. Right? You understand? When something happens. So what voltage will we use to calculate the size of that resistor? Will we use the minimum? 2. You're exactly right. Because if I use 2 and the voltage goes up, the Zener's gonna conduct more current. We don't want it to conduct. If we use 5, if we calculated it to drop 5, if it dropped down to 2, then we're going to go out of regulation, right? You understand? If I calculate it for 2 and it goes up to 5, IZK is going up. Zener current's going up. IZK is not. Y'all understand that? So what size resistor would I use? So let's see. So what we got to do? We got to come up here and we're going to say, okay, what would RS equal to? So we're going to use VRS minimum. Okay, what's our currents? So that's our voltage. Everybody okay there? Did that make sense so far? So if you can logically figure this out, all we're using is what law? Ohm's law. R is equal to V over I. So we figured out which voltage we're going to use. Which voltage are we going to use? We're going to use the minimum voltage. Well, yes. So we're going to say 2 divided by 101 milli. Okay, you understand that? Okay. And I think we need to increase it a little bit. Let's do it that way. Yeah, we got to. Why we got to add them? Because that resistor sees those currents. It's a series resistor. And so all the current flows through the resistor. So what do we come up and get? 1,980. Because there's no such thing as a 1,980 ohm resistor. And we went on, huh? No. If I go to 2K, current goes down. We go back into the need. So what are we going to always? I don't care if it falls on a resistor. If it falls on a 200 ohm resistor and there is a 200 ohm resistor, we are not going to use a 200 ohm resistor. What are we going to do? We're going to always do what? Go down to the next standard value. And then check the tolerance. Because we always want to move it away from the need, right? Y'all understand that? So most people have a tendency, they say 1,980 ohms. They say, well, that's something close to 2K. But understand, this guy right here supports 1 milliamp of IZK. We want more. So what are we going to do with this series resistor? Huh? If there's a 1.9K, I wouldn't use that one. I'd probably go down at least 2 sides. If it's on close on one, I'd probably go down at least 2 sides. We got a standard resistor chart. You got one? Yeah, 1.9K, there's probably a standard. That only gives me 80 ohms worth of safety. So we'll probably go down to the next standard value. And then we'll check it. Y'all look at y'all's formula sheet. I think we increased this by. I'm trying to remember the recommended. So y'all should have Zener regulated power supplies, idle load max plus IZK. Round down and check tolerance. So,
I did that wrong.
yeah, 1.9K sounds a little high, but I wouldn't know. $19.8 ohms. You did micro. So what size resistor would we use? I'm gonna go to the blackboard. This is on y'all side. And then I'm gonna go to oops, let me go. I think this is in handouts. Data sheets, reference material, glossary, standard resistor chart. So this is a standard resistor. And usually originally you can't hardly find 10% resistors anymore. About the best you can do is 5%. So what do we come up and get? 19 ohms. Okay, so what would we use? Well, we could. Let's check this. So 19 ohms. Let's check the tolerance and see if it comes up. So what we do is we check the tolerance. So we don't need to worry about the low side. We need to worry about the high side, right? Everybody okay? So what I would do is I would take 18. 18, I'm going to multiply that by 1.05. That automatically increases it by 5%, right? You understand that? And what does that come up and give me? What's that? 18.9. Yeah, we could use that one. So we check so that's what you got to do. You got to check your tolerance, right? So even if it's on the high side tolerance, we're not worried about the low side tolerance. We're worried about the high side tolerance. Okay, what else do I need to know about that resistor? So we know we got a 5% resistor. We know we got a 19.8 ohm. Oh, I'm sorry. We got it. So I'm through with this, by the way. So this is the resistor we use. So all your other calculations are going to be for that size resistor. So what else do I need to know about that resistor before I order? What else? The watts. So what would be the wattage rating on that? Well, what we need to do is we need to figure the maximum current that would ever flow through that resistor. So when would the maximum current flow through the resistor? When it's dropping 5 volts and when it's dropping 2 volts? When it's dropping 5 volts or dropping 2 volts? Come on, come on. I'm killing you. If voltage goes up, current goes up. If voltage and current goes up, power goes up. So this is best to use one of our. So I'd say PR would be equal to V squared. So I'd say 5 squared over whatever the maximum over the size of the resistor. 18.9. They're gonna give me a heart attack, guys. Here we're not talking about the source. We're talking about the load, right? You understand? And this is what gets a lot of people confused. So when we're talking about the source, we say the higher the voltage, the lower the current. But when we get to the load, if the voltage goes up, the current goes up, and the voltage goes down, the current goes down. When we're talking about that power, we're talking about the source. But once it hits the load, then Ohm's law is Ohm's law. So V squared over R is probably the best one to use right here because you don't have to calculate current. So what do you use though? You use the what? The maximum voltage over the size of the resistor that you choose. Not the one you calculate, the one you choose, right? You understand? So what power rating would we need on this resistor? 25 divided by 18.9. 1.3, so we'd use at least probably a 5 watt. Because you need to double it. You need to double the power rating on that, right? You understand? And then choose the next higher standard. So we calculated a Zener power supply. We just got to figure out, we're going to take a break. We're going to figure out if we're going to burn the Zener up. This is so neat. So the input goes up 5 volts. What would the current flow be at 5 volts? So IR at 5 volts is going to be 5 divided by 18.9 ohms. So what would the maximum current flow be through IR? So this is our max. What would the maximum current be? 265 milliamps. So 265 milliamps. What's the current flow through the load? What's it going to do? Is it going to go up? Is it going to go down? Is it going to stay the same? Well, if the voltage drop across it stays the same, the current flow through it will stay the same. So what's going to happen is my Zener current is going to eat up whatever's left. So my Zener current is going to go up to what? 165 milliamps. So guess what we just did? So this would be a poor design. We just burn our Zener up. So your Zener, what it does, it adjusts its resistance to maintain this guy out here at the same value because it maintains the voltage. So if the current flow over here goes up, the Zener current goes up. If the current flow through RS goes down, Zener current goes down. So right now, if we're doing 265 milliamps, this guy right here is getting 100 milliamps. This guy here is getting 165. That means 10 power. 10 times 165 is 1.65 watts. What's the Zener rated at? 1 watt. What did we just do? We burned up our Zener. So what does that mean we need to do? It means we need to find a Zener that has a higher wattage rating, right? So these guys work real good, but the range of currents that they can handle is still very small. But later on, what we're going to do is we're going to hook this thing up to a bipolar junction transistor. And that sucker can give us a lot of current gain. Well, if you lose a loader arm resistor, it burn up faster. If you go to a loader arm, this guy's going to drop 5 volts. If you go to a smaller resistor, it's going to conduct more current. If it conducts more current, that means this guy's going to keep trying to do 100 milliamps. This guy's going to try to make up the difference. So if you go to a smaller resistor, this current is going to go above 165. If we use a bigger resistor, that means we're not going to get this 1 milliamp, which is called IZK, right? You understand? If we don't get IZK, the Zener goes out of regulation. So we don't have the only option we got, if I want to get this right here, if I want to get this, then I've got to use a Zener that's rated more than 1 watt. So I could get a 2 watt Zener, and it would work fine. So that's the other option you got, and that's why you calculate this out. So what you do is you choose a Zener, and then you say, well, does it work? If it don't work, then you do what? You just find one that's got a bigger watt. Because we can't do anything with that resistance. Because if I raise it up and we go below 1 milliamp, the Zener goes out of regulation. If I go down, we're surely going to burn it up, right? So calculating that resistor depends on this guy right here too. So that's why when we do all these calculations, we come back and always check to see if we're going to burn up our Zener. If we don't exceed the wattage rating on the Zener, then it's okay. But what laws have we used? What to do? Now this is a dynamic device. This is not a resistor. This guy literally changes its resistance to maintain a constant voltage across the source. It automatically does that for us. But what laws are we using? We're using Ohm's law. We're using Kirchhoff's law. We're using Kirchhoff's voltage law. We're using Kirchhoff's current laws. We're using Watt's law. So we're using all the laws that you already know. All we're doing now is taking these formulas and adapting them for something that's dynamic. These things are not fixed. These things are dynamic, right? You understand? So when I get into bipolar transistors, these guys amplify power. They don't create power. They manage power. So that means if I've got a 500 watt amplifier, my system in my car has got to give me over 500 watts. So that amplifier does not create power, it manages power, right? You understand that. But now I can take, and what laws are we going to use to calculate most of those things? We're going to use Ohm's law, we're going to use Watt's law, we're going to use, that's the formulas we're going to use. We're going to use series circuits, we're going to use parallel circuits, and then we'll throw a couple of more in there that deal strictly with transistors. But you've almost learned your formulas for calculating these things. All you got to do is figure out what V to use and what I to use, right? You understand? To figure out that voltage drop. And this is what's so neat. So back in DC, what do those things do? Those suckers make heat. That's what they do. That's all a resistor does for you in DC. Here we're using resistors to manage these solid state devices. So these resistors in there for a purpose, but they're not in there just to make heat anymore. So what's the function of this resistor? This resistor drops the difference between our unregulated and our regulated. And it's up to you to choose the right one. You got one or two things. You can calculate it, or you can do what we call swap them until they work, right? Y'all take a break. But ain't this neat?